All right, so let's go take a walk through on this weld layer problem that we looked at in class. And the idea here is that we have a very thick plate that we've welded together with another thick plate. So we essentially have two semi-infinite solids on either side of this weld layer. And in this particular kind of problem, we're just treating the weld layer as if it's the same material in terms of the diffusivity, so we only have one diffusivity. So in this case, we're going to start off with 1 weight percent in this weld layer. We're going to have 0 out in the semi-infinite regions. The weld layer has a thickness total of 2 millimeters. And let's see what else we got. We got the diffusivity here, you saw that. And what we'd like to do is to go ahead and use finite difference to calculate the concentration profile after 60 minutes. Okay, so this is sometimes referred to as an encapsulated layer problem, or we have a layer sandwiched between two other materials. And a more advanced type problem would allow the diffusivity to perhaps be different in the encapsulated layer versus outside of the other material. In this one, again, the diffusivity is everywhere the same. All right, well, this kind of problem can be solved analytically, and this is the solution to it. And you can go ahead and plot this one in your homework and compare it to what we're going to do here in the finite difference case. And then for part C in our problem, we want to find out how long it takes for the concentration in the weld layer, this 1 weight percent, to reduce by 95%. So in other words, we want to find out when the node that's in the weld layer in the center of it reaches 0.05 weight percent. So those are the problems. So let's go ahead and try and set this problem up. This is the picture idea of what we're given. We have this weld layer 2 millimeters thick, and it's sandwiched between two semi-infinite plates. Okay, so we don't have dimensions on those. Those are thick enough that we don't have to worry about our concentration as it starts to diffuse into these regions ever reaching the other side of the plate. All right. So one of the things I want you to notice here is that there's symmetry in this problem. So if I was to look in the center of this weld, what I see for the concentration as it starts to move into this plate is going to be identical to what happens on this side. Okay, and that's important because that means that when we do this in finite difference, we only need to take and look at this right half. Okay, and I can do that by putting a node directly on this line of symmetry. So let's see how that goes. Oops. All right, let's see. Here we are. Okay, so here's our picture again. And now I just want to show it to you in terms of some node placements, thinking about that. So if I was to try and do the whole problem, okay, then I could have a node sitting here in the center. I'm going to call that C1. And then as I move to the right, if I use a spacing, say, of 1/2 millimeter, then when I move to the right, the 1/2 millimeter is going to be in the middle of this region to the right side. And then another 1/2 millimeter will put me on this interface between the weld and my sheet. Right, so I've got C2 then sitting there, and then C3 would be putting me right on the edge here again of the weld and the sheet. So that means C3 is going to have 1/2 of its volume here, right, in the weld layer, and 1/2 of its volume in the sheet. So getting this picture correctly and putting the nodes on there directly on the picture is really your first step in how to interpret everything. So noticing that the volume here is 1/2 and 1/2, then when I do my starting conditions, then I'm not going to be using 0, I'm not going to be using 1. In fact, it's 50-50, so therefore I'm going to be using 0.5 as my starting case. That's my average concentration in this volume. And that node represents the entire volume, so I need that average concentration. Okay. And that's what you see here. My node 3 is at 0.5 to start. My node 1 and my node 2 are at 1 to start. Okay. And then from 4 on, I'm 0 to start. Okay. Now, I only have node 1 here. I didn't bother to put the nodes to the left. I could, so I could have a node 2, 3, 4, 5. Notice I'm using the same node numbering because they're symmetric. So this node here to the left is identical to what I'm going to get for this node here. Right? Likewise, if I go 2 over, that's going to be the same as 2 over on this side. And so I've numbered these to show the symmetry. So rather than trying to do all of these nodes, which is going to be a real problem, especially in this case where I don't know how many columns I need yet in order to satisfy this semi-infinite solution, it's much better, much easier to just go ahead and put a node here and only look at the right side of this problem. All right, now remember, with our semi-infinite solution, what that really means is that when we get to the time step that we're interested in, that if I come out here and look at these columns out here on the right, that they're still going to have a concentration of 0. And I want a few columns out here to have that value. And then that suggests that my sample is thick enough, I have enough columns, that this diffusion process hasn't reached that far into the sample. So we'll take a look at that in a second as well. But this is my node setup, and so that's really the first step. And it's critical that you either have some sketch that you draw and number so that you can think through the problem. Okay? Because this tells me everything I need to know. It tells me where my symmetry is. It tells me if I color code it. It tells me what concentrations to use. I can see that this one is 50-50, so that tells me, okay, well, I'm going to use the average there. And so all of my information is in here, and it gives me my length scale. All right, so let's go ahead and take a look at what we put in now for the nodes. So if this problem had 2 different materials, that was defined as having 2 different diffusivities. So if this was really material 1 and this was material 2, and you were given a diffusivity 1 and a diffusivity 2, then when I did this problem down here, the equation for node 1 and 2 would be using the diffusivity for material 1. So it would be using Fourier 1. The diffusivities out here being diffusivity 2, these would all be using the diffusivity 2 all the way out. Okay? This node, C3, would be an interface, and it would be using our interface equation, which has diffusivity 1 for the influx and diffusivity 2 for the outflux. Okay, and you can see that in your class notes for that interface. This problem, we only have one diffusivity. Okay, so although we can call this a kind of an interface node to start, because there's a difference between the weld and the rest of the sample, once we start progressing, this interface is going to go away. Again, we only have one diffusivity, so we're still going to just use a regular internal node equation. If you went and used the interface equation here, that's perfectly fine. It's just that you're going to use the same D on the left as you do on the right, and so that interface equation will simply become the internal node equation. All right, so all of these then are going to be internal node equations. So let me just click on one and show that. Okay, so I'm looking at node 3 here at my first time step. You can see that my node 3, if I look at the color coding, it's going to look at G20, which is to the left. It's going to look at H20, which is node 3, and I20, which is node 4. Okay, so this is my typical internal node equation. So I do that once, and then I can copy across, and I can copy down. Okay. And that's the same equation that's going to be in any of these. It's going to be in node 2 as well. It's the same identical equation, and uses the same Fourier number because we only have one diffusivity. Okay. But again, it looks to the left here. It looks to the node that I'm looking at, node 2, and it looks to the right, node 3. Okay. So those you've seen. Now the question is, what do we do with node 1? Okay. So when we put this into Excel, one of the mistakes is that since it's the starting node, people often think of this as being a surface. Right? This is where our image helps, our sketch, to determine what it is. Hey, this is not a surface like it normally is, because I can see right here, this is not a surface. Right? This is a regular internal node, just like all the other ones. Right? My surface nodes would be out here at infinity somewhere. So it's still an internal node. So I can take this internal node equation at 2 and just copy it over here to this node 1. So let me go ahead and look in this node 1 now. So when I look in it, notice that my internal node equation wants to look to the left. Okay? And that's where I have a problem. Now there is a node to the left, but in our sheet, we cut it off. We didn't include it in our calculation. Okay? So we have to fix that. So this wants to look to the left, and notice that when it does look to the left, that's simply C2. It's identical to this one because of the symmetry. So rather than have it look here to the left, we'll just simply change that one to look to the right instead. So in other words, up here when it says E20, okay, that's again to the left, I want it to say G20 because those are identical nodes. So I'm just going to change that to G20, and now it's going to look here twice. Okay, so I move the left one to simply look to the right. And that takes care of my problem that I cut off this node here that should otherwise be there. So let me go ahead and enter that. And that's all I need to do to fix the equation for this one node. And of course that equation then is for all of node 1, all the way down. Okay. So in your text, when you look at the symmetry node equation, you'll see it's written slightly different here. Okay, these two terms are combined so that you've got 2 times G20, and then the 2's were factored out. So there was a 2 out front, and then in here we would just have G20 minus F20. Okay. So you can use that, or you can use this method. I kind of like this one because all I have to do is write one equation. Everything is copied. I copied it over here as well, and then I just fix that one left node and then just copy down. All right, and so that really is all there is to this problem, is fixing that equation here. So again, we know it's not a surface because of our sketch. Okay, this tells us everything. It's an internal node. It also tells me that when I want to look to the left, that's C2, which is right here to the right. And so I just change it. And that's it. Then I just go ahead and put in my initial conditions and just run this. All right, now we talk about this issue about this end being semi-infinite. So in this problem, one of the things we wanted to find out is how long does it take for this weld layer, so the center of it here, which is node 1, to go down to 0.05. And so in this problem, if I just keep scrolling down, see I'm at 0.2, I'm going to have to go way down. So let me go down, I got 0.8, 0.06, 0.05, almost there, boom. Okay, there we are. Okay, so this is the first spot where my center finally reaches 0.05, which is what I wanted to find out. Okay, that's like 29 days. Notice I got 4,000 rows here in this problem. All right, so I got to check one thing, and that is, do I have enough columns so that my last several columns are still at 0? Right, that's my semi-infinite condition. So if I scroll them out here, all right, it looks like, well, one, I've got plenty of columns, but it looks like I could have stopped. So maybe somewhere in here. I think I only need to probably go out to dy. That gives me a couple of columns here that are still at 0. So this tells me that my concentration hasn't reached this far into the material. And so I'm not affecting things out here. If I was to fix this cell, of a value 0. Okay, and that's really all that I need for that semi-infinite case. So if I go up here and look, I can see how many that is. So in this particular case with my variables, this is 124 columns. Okay, that's a lot of columns. I think I had a bunch more just because I didn't know how many I needed, so I just kept dragging it. I have 186 columns. But whatever your last column is, notice that this one is fixed at 0, right? I'm not using an internal node like I am at 185. I've got to do something with this one, and so I fix it at 0. Okay, and again, that doesn't affect my solution being fixed at 0. As long as these columns here remain at 0, then this is not affecting anything. If these were all to start changing, and there is some concentration here, then making this 0 would mean I'd suddenly have a flux from 185 into 186, and I would be moving material out of my material, and so it's no longer my semi-infinite case. All right, so that's the one part. The other part of your problem was to plot this equation, and so the way that you can think about doing that is just give yourself a column of x values. I went and used the same spacing, 0.5 millimeters, as we do in this problem, so I can compare them. To do the problem, I'm going to need to put things into meters because my diffusivity is in meters. Next thing I'm going to do is calculate x star. So x star is x divided by delta. Delta is my thickness, 1 millimeter, okay, or in terms of meters. So x star here is just simply x divided by delta. Don't forget the $2 signs so that this is a constant and you're not moving where it's looking as we copy down. All right, next thing is C star. C star is calculated directly from this equation. Okay, so you can see there's my equation here. So I've got in this error function, it's 1 minus x star, which is this column. So as I copy down, it'll use the new values. And then on the bottom is the T star. The T star here is also a constant. It's defined as my diffusivity times time. And in this problem, we were doing 1 hour. So we're going to be putting in 3,600 seconds here. And then the delta again is the 1 millimeter, or 10 to the minus 3 meters. And so here's my T star calculated that goes into this equation. Again, it's a constant. And so we will use the dollar signs to make sure that we're not moving it as we copy down. All right, that's my T star. And then I want to actually plot C. And so C star was defined as C, which I want, minus C0 over that encapsulated layer concentration minus C0. In our problem, C0 we set equal to 0, and so that falls out. And then the concentration in the weld layer was just 1, and so in our case, C star is equal to C. Okay, but that's not always the case in a general solution. All right, but now I can go ahead and plot C, and I can plot my x value, and I can then include that straight on my finite difference plot. All right, that is the end of this problem. I guess the only other piece maybe is how do I include that plot on here? If you have trouble with that, I can just show you that real quick. So what I did was first to make my plot using the row data that I needed. Okay, that you've done before. Once that's made, then I can go in here to this plot here, and I can go and select chart design and select data. And so once I'm in this place, then I can go ahead and add. Okay, and what I want to add is my calculation there for C star. So my x values, I'm just going to scroll over. Okay, and I would go ahead, once I'm in here, I would just pick my x values, and then delete what's in this y piece. Then for my y values, that would be my c. So I'll go ahead and scroll down there. And these should be the same numbers. So I went down to 41 here. So I do have to make sure that I go down the same number. They have to be equal. All right, those are my two, and I could give it a name if I want, like analytical. I'm just going to do, and then I just hit OK, and that adds it in. Okay, so I've already done that before. That's where this one is. But that's how you can add it in. Just say OK, and then you'll have it over here in your plot. Okay, so now I've got a red and a green, and they're directly on top of each other. It's the same data. Okay, and then the 60-minute one is my finite difference data. Okay, I hope that helps.